Now I'm going to talk about observer design. So how to pick this gain L such that the error of the system goes to 0. And remember, the error E is the difference between X and X hat, where X hat is the state estimate of our system. So to do this, we can use this theorem, this result called the Cayley-Hamilton theorem, which essentially says the matrix A minus LC must satisfy its own characteristic equation. Okay, so the characteristic equation is, again, the eigenvalues that we want our system to satisfy. So essentially what we can do is we want to find L, right? We have A, we have C, and then we have the eigenvalues that we want our system to satisfy. So we plug in the matrix into our characteristic equation, and then we evaluate that, and then that'll give us the result. So again, the characteristic equation here is, we kind of call it alpha of S is equal to alpha 0 plus alpha 1 S plus alpha 2 S all the way out to alpha to Sn, and that's equal to 0. Okay. So then because of the Cayley-Hamilton theorem, we have that alpha of ALC is equal to alpha 0, and I'm just plugging and chugging now. Alpha 1 A minus LC plus alpha 2 A minus LC squared plus A minus LC to the n. Now we want this guy equal to 0. And so now, if you notice, we have several powers of matrices here. So now we have to evaluate what those powers are. So the powers of A minus LC are given by So let's start with, we don't have to start with A minus LC to the power of 1 because that just is. But we start with A minus LC squared, okay? So this will be equal to, again, A minus LC times A minus LC, which is equal to A times A minus A times LC minus LC times A minus LC LC. Okay. So an easier way to write this would be A squared minus ALC minus LCA minus LC squared. I have to tell you, this is the second time that I've done this talk, because about more than halfway through, I was on a good roll, making good progress, almost done with the talk or the section. And then my dog was sleeping on the couch right here, and he just rolled over and fell off the couch, and he whimpered and cried. And I'm like, oh, now I have to stop this and I have to take care of him. And so this is take 2. Hopefully it's going better. I think it is. But it was, yeah. So he totally messed up my flow. But here we go, on with the show. So next is A minus LC cubed, okay? So again, that's A minus LC, times A minus LC times A minus LC. Okay, so then this guy is equal to, let's just start with using the results from the last one, which is equal to a squared minus LC. Actually, yeah, so we're going to take a step back from the last one. And then this will be L times A minus LC times LC. And then this whole quantity times A minus LC, right? So then the next line will be A cubed minus LC A squared minus A minus LC times LCA minus A squared minus LCA minus ALC LC times LC. Whew. All right, then we can combine like terms so that we get A cubed minus LCA squared minus A minus LC LCA minus A minus A minus LC squared times LC. Make that L and C actually distinct, LC. All right, then we can keep doing this all the way out. And if we notice here, we have some similarities. So here we get some things keep popping up, right? We get A cubed, then we get A LC to A squared, and then we get A minus LC times LCA, and then we get an ALC squared times LC. So it turns out that if we go to the nth order, it turns out we get A to the n minus LC A to the n minus 1, okay, minus A LC A to the n minus 2 minus all the way out to ALC n minus 1 LC. Okay. Hopefully it made sense. Okay, so now let's plug in those quantities to our characteristic equation here. So now we have L squared, L cubed, and A minus LC to the n. Let's plug it into this characteristic equation here and see what we get. So it follows that we get that alpha, the characteristic equation of L minus A minus LC is equal to alpha naught times I. And I'm going to write it in such a way that it'll start to make a little sense. Plus alpha 1 times A minus LC plus alpha 2 A squared minus LCA minus A minus LC times LC plus A cubed, alpha cubed, A cubed, which is equal times A cubed LC A squared minus A minus LC LCA minus ALC A minus LC squared LC. And then you can take it out, plus dot, all the way out to AN minus LC A n minus 1 minus A minus LC LC A n minus 2 minus minus A minus LC n minus 1 LC. And then this quantity is equal to 0. All right, and so then we can notice that we can rearrange the system such that we can pull out different parts of it. So we get, if we look at this, we get alpha A minus LC. And if we look at this, we can come back here and we get alpha is not times I. We get alpha 1 times A, alpha 2 times A squared, alpha 3 times A cubed, and A to the n. So let's pull that out. So we get alpha naught plus alpha 1 A plus alpha 2 A squared plus alpha 3 A cubed plus alpha n. So we get this guy, and then we get this quantity minus alpha 1 LC minus alpha 2 times LCA plus A minus LC minus alpha 3 times LCA squared plus A minus LCA plus A minus LC squared LC, and so on, equals 0. All right. So then go to the next page here. We get that this implies that alpha of A minus LC is equal to, again, alpha naught I plus alpha 1 A plus alpha 2 A squared plus, oops, A squared, not cubed, alpha 3 A cubed plus alpha n, or A to the n, minus alpha 1 L plus alpha 2 A minus LC times L. And this is just rearranging terms. Alpha 3 A minus LC squared L plus times C. And then this guy minus alpha 2 L plus alpha 3 A minus LC times L plus all the way out times CA. And then the next quantity is minus alpha 3 L plus, and hopefully we're starting to see some similarities here, times CA squared. And then we can take this out, we go minus dot 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 minus L times CA n to the minus 1. All right. And then this quantity is equal to 0. Okay. So if we inspect this here, we have this quantity here. Okay. And then we get that because we rearranged everything, we pulled out a C here on the first one. We managed to pull out a CA on the second one. On the third one, we pulled out a CA squared. And then went all the way down, we pulled out a C. This should be a CA to the n minus 1. Make sense? So what is that? Where have we seen that before? Right? Well, in fact, we saw it in the observability matrix. Okay, so this is actually going to be able to wrap in the observability matrix that we found to determine if our system is observable or not. and we can actually use it to design our observer game. Okay, so let's get back into it. So then we can make the following substitutions. Oops. All right. So we can get alpha A is equal to A naught I plus A1 A, oops, alpha 1 A plus alpha 2 A squared plus alpha 3 A cubed plus alpha n or an. So that we can define that. Well, that's by definition, right? By definition of A, and A must satisfy its own characteristic equation. So then we get H, and you can call H is equal to alpha 1 times L plus alpha 2 times A minus LC times L plus alpha 3 times A minus LC squared times L plus times C. And then we get alpha 2 L plus alpha 3 A minus LC times L plus times CA plus alpha 3 times L plus all the way out times C times A squared dot plus L times C A plus A to the n minus 1 power. And let's put this in parentheses. All right, so now we have H is equal to, if you come back up here, H is going to be equal to this guy over here. Alpha of A is equal to this top quantity here. Am I frozen? Maybe it'll fix itself. Here, it's catching up. Okay. So alpha is equal to this top quantity here, alpha of A, and then this bottom quantity here is equal to H. All right, so now let's keep going. All right, so then, because this is all equal to 0, or this guy is equal to 0 above, this guy is equal to 0, when we get down here, that we can split up H. So let's clear this guy. So it turns out that we can split up H in such a way that we get in a matrix form. This will be alpha 1 times L. Let me do it this way, cleaner. All right, so then this will be equal to alpha 1 L plus alpha 2 A minus CL times L plus all the way out. Put a comma there. Alpha 2 L plus alpha cubed, alpha 3 A minus LC times L plus comma times L, and then this guy times this matrix, which you've seen before, CA squared down to CA n minus 1. Neat. All right, so then it implies that if we can take this matrix right here, and call this J, this is our observability matrix, which I defined it as L in the previous lectures, but I realized that was a bad notation. So I'm going to call this as calligraph O. or just, let's just do O, not calligraph O, yeah. Yeah, let's do O bar to distinguish it between 0 and O. Okay, and then this guy, let's call J. So then we get that H is equal to J times O bar. And as a result, so then we can say, if we bring it back to our original objective here, which was determining the characteristic equation of A minus LC, this guy is equal to alpha, the characteristic equation of A, minus J times the observability matrix O bar. And this guy is equal to 0. So this implies that J is equal to alpha of A times O bar inverse. All right, so then notice that we'll only care about finding L, right? So if we come back up here and look at our system, we can see that some of these terms have only L explicitly in them, and it happens to be the very last term here. Or if you look over here in J, the very last term of J. So if we want to single out L, what we can do is that, so what we want to do is the goal is to find L. So, and then this corresponds to the last element of J. Okay, so we've isolated J. We've isolated J right here. Oops. Isolated J right here. So now to get L, we just have to multiply by a matrix to pull out L. So if we do that, let's go ahead and come back down here. So what we can do is we can say we have J, and let's multiply it on the right-hand side by a matrix 0, 0, 0, 0, 0, 0, all the way down to 1. I guess I don't need that many zeros. As long as the last value is 1. 1. Okay? This will be equal to alpha times A times the observability matrix inverted. Again, multiplied by 0, 0, 0, 0 down to 1. Okay, and we're allowed to do this because we're doing it on both sides of the equality, right? Okay, so then as I showed before, this quantity on the left half side is equal to L. So this will be equal to L is equal to alpha A O bar inverse times this matrix 0, 0, 0 down to 1. Okay, and so this is called the Ackermann's formula for the state observer. So I just had a couple more things I needed to say on Ackermann's formula. So again, L is equal to alpha A O bar inverse times this matrix 0, 0, 0, 0, 0, 0, 1 is, oops, what's called Ackermann's formula for state space observer. Okay. However, there's two caveats. Two caveats. One, the eigenvalues of A and A minus LC must be disjoint. Okay. Two, the system must be observable. So that means that the observability matrix must be what? Non-singular, right. And this is so we can take the inverse of it, right? Great. And so next I'm going to do something very similar, but for control design.